Okay, hello everybody. Welcome to our seminar. It's my pleasure to introduce today's speaker. This is Professor Joli. I'll say a few words about Professor Joli because there are people who are not able to attend today's ceremony. He was honored by university as a doctor honoris causa. Professor Joli is full professor in University of Köln. He's a director of Institute for Nuclear Physics. His interest research area is experimental and theoretical nuclear structure. A lot of achievements which are worldwide recognized. Also, maybe it is of interest of broader audience. He also wrote a book, Symmetries in Atomic Nuclear from Isospin to Supersymmetry. And I don't want to waste more time. So, yeah, please.
it's hard to manipulate, but once you can manipulate it by complex instrumentation, then it's very generous in the number of information or observables you can get from it. And so let me illustrate this by the tandem accelerator, which we have in the university in Köln. So you see, this is a huge, complex thing, which you need to accelerate ions to high enough energies such that they can overcome the Coulomb barrier and penetrate the atomic nucleus, where they then make a nuclear reaction, forming a new atomic nucleus in a very highly excited state. And if you have formed this new nucleus, then you need detectors. Here you see some of our germanium detectors, which are then used to measure the electromagnetic radiation or the gamma rays emitted by the atomic nucleus after its excitation due to the nuclear reaction. And there it is very generous because you get a lot of different gamma ray transitions. Here you see a germanium spectrum and you see all these different lines in the germanium spectrum. And so now you have to solve the puzzle to place the lines in a level scheme that you do by coincidence measurements, and then also to determine, for instance, lifetimes, branching ratios, and other properties, multipolarities of this gamma ray emitted after from the excited nucleus. And so that's what we do experimentally in Köln. So after you create an atomic nucleus, then you have relatively, it's a very complex system, very complex strong force, but nevertheless, you observe simple collective motions. The oldest one is the shell model structure. So this was found already in the beginning after the Second World War, that an atomic nucleus exhibits, like the atom itself, closed shells. You have outside the closed shells, you have valence. So hi again. So if you now have many of these nucleons, then you observe another simple model, which is the collective motion, in which you can now describe the atomic nucleus as a kind of quantum liquid, which can make vibrations and rotations. And here also I can introduce for the first time something important, is the nuclear shape, whether it's spherical, whether it's deformed, oblate or prolate, and so on. So that will occupy us. But first we will now use the fact of the pairing force or the Cooper pairs in order to introduce the interacting boson approximation. Now, we will not have a distinction at the moment between neutrons and protons. We will treat the neutron and proton pairs as being just bosons. And now if you go to second quantization and you assume that you have only one body and two body interactions, the most simple Hamiltonian you can form is given here. So this is the Schrödinger equation in second quantization. I should not touch the screen because then it does something. So you have here the relation to the first order quantum description. You have the creation and annihilations operators of the bosons, so S or D bosons. And we assume, very important, that N is a constant. It's given by the number of valence nucleons. So if you do that and you write the most general Hamiltonian in second quantization, and you now introduce angular momentum coupling, you get this simple form. It has 5 parameters, and there is 1 parameter hidden in the quadruple operator. So you describe the most general N, S, and D boson with second and first order interactions by a 6 parameter Hamiltonian in second quantization. Now, something which is important, which I will not explain in this talk because it will take a whole talk, are dynamical symmetries. Suppose you have this Hamiltonian with S and D bosons, and now you remove all the S bosons from it. First of all, I have to mention, S has 1 magnetic substate, L equal 2 has 5 magnetic substates. So this makes that your model Hamiltonian is U6 with N as the irreducible representation of U6. Now, remove all the S bosons, then you have a Hamiltonian having only D bosons, and you get a reduction to a group having only 5 dimensions, the magnetic states of the D boson, and so you get a reduction from U6 to U5. And then finally, what you observe is when you don't have a magnetic field, then you observe the angular momentum as being the fundamental experimentally observable quantum number. And now you can make a nested group chain going over U5, O6 to SO3, and this is the first dynamical symmetry. A dynamical symmetry is something important because it allows you now to rewrite some terms of this Hamiltonian. And the important thing is, in a dynamical symmetry, you still have parameters, but the parameters do not influence the wave functions. So independent of which value of the parameter you have, your wave function will always be the same. So that's a very strange property, but that allows you to make, independent of the parameters of the Hamiltonian, predictions for all observables in such a dynamical symmetry, analytic predictions. For instance, for BE2 values or transfer intensities. Now, the SD boson system has 4 different dynamical symmetries. 3 of them are normally mentioned, U5, O6, and SU3. SU3 is the symmetry of a rotor, and this describes then rotational nuclei. This is vibrational nuclei, and this is something in between rotational and called gamma unstable nuclei. So normally you have this red tree once in all textbooks, but there is a fourth one, which is important in this talk, which is the SU3 bar symmetry, which does not describe prolate or cigar-like rotors, but oblate or pancake-like rotors. Now, of course, this is very nice group theoretical, and it's very nice. The important point is that there are atomic nuclei which resemble these dynamical symmetries. One example is 110 cadmium, in which you have here a comparison between theory and experiment for the normal states, not kind of particle hole states, which are observed in this energy range, but which are now left out. And you see this spherical vibration, 1 vibrator, 2, 3, 4, and so on. Another example, which is very important for the history of the model, because you had this 0.6 limit. This was some extra coming out of the analysis of this Hamiltonian, and it was not corresponding to anything at that moment. Later on, it was found that this was realized in platinum 196. There you see the comparison between the 0.6 spectrum on the right side and the experimental one. And so it's discovered by Czyzewski and Karsten in 1978. Also, it was shown by Meyer-Terfven that it had a corresponding in the collective model, this gamma unstable rotor. One thing which is important, as I said, wave functions give predictions independent of the parameters. It is one of the predictions is that this transitions from this 0+ state to this 0+ state, no, from this 2+ state to this 0+ state, BE2 transition is forbidden. And this was observed in 1990 using this method, which I explained this morning, the grid method after neutron capture. And it was observed then in 2015 in the Excel campaign once more, showing that this BE2 value is very small, which is important to justify the use of this model. Now, let's go to the simplest Hamiltonian we can imagine. So we just take the eta term with the ND term, and we take the quadruple interaction. We weight both terms with this eta term. If eta is 1, then this is switched off. We only have this term. If eta is 0, then we only have this term. We have an independence, which we take account because here you have 2 times the quadruple. Here you have only a one-body operator. And then we have a scaling factor just to scale up everything comparing to experiment. Again, the quadruple interaction contains a second parameter, chi, which is here in weighting the SD and ds term compared to the d-decker d tilde term. So this Hamiltonian has 2 structural parameters, eta and chi, and a scaling factor. Now, the interesting thing, this is our Ising model, more or less, in nuclear physics. The interesting thing is that the first term generates spherical shapes, so a round nucleus. And the second term generates a rotational or a deformed shape. So by changing eta, we can now weight in how far we want to have a spherical shape or in how far we want to have a deformed shape. Moreover, these 2 parameters, I don't consider A, the scaling factor, as a parameter. It just blows up and shrinks the complete level scheme. So this 2 parameter Hamiltonian has 4 dynamical symmetries. So it represents, in some sense, the complete IBM structure you can have. So if we take eta equal to 1, we don't have the quadrupole term, and you have only d-decker in the Hamiltonian, so you have the U5 limit of the model, which you can apply. If you now take eta, this is the Kasten triangle. It has 2 axes. One is eta and one is chi. So if we place now eta equal to 0 on the Kasten triangle, then we are sitting here in this corner, and we can now go on to the second case. Eta is equal to 0. And chi equal to 0. Now this corresponds to the gamma unstable or the O6 limit of the model. So if we fill it in on the triangle, we get here chi equals 0 and eta equals 0. And so we have here the O6 dynamical symmetry. If we now continue, we can get a special value, which is the square root out of 7 multiplied with -1/2. This is the SU3 limit of the model. So a prolate vibrational nucleus is sitting here on this triangle. And finally, the oblate one, which has plus the square root out of 7 divided by 2, is situated on the last corner of our triangle. So we have a very simple Hamiltonian having a spherical symmetry dominating part, a deformed dominating part, and it has 4 dynamical symmetries. Now, we want to discuss nuclear shapes, and they are associated with the 4 dynamical symmetries, and they can be studied using the coherent state formalism. In this sense, you have an energy functional, which will now depend on n, eta, and chi, and on the parameters alpha mu, which are depending on the deformation. So you can use the intrinsic variables beta, which is a quantity, and gamma, which is an angle, to determine these alpha coefficients. If you do that, then you get beta cosinus gamma for D0, and then beta sinus gamma for the plus or minus 2 parts of the D. So that we will use now in order to use our simple Hamiltonian and to extract from it a kind of associated shape. Now, especially for the people who are non-nuclear physicists, if you use these Bohr variables beta and gamma, so here they are plotted, beta is going in this direction or even in this direction, and gamma is an angle which goes from 0 to 360 degrees. So if your gamma equals 0, you get a cigar kind of structure in the direction of the z-axis. If you have 60 degrees, or p divided by 3, you get an oblate structure, a pancake structure, but now with respect to the epsilon axis. And if you continue, you get again a prolate with the x, and then an oblate with the z, and so on. Now, it doesn't matter how x, epsilon, and z are defined. And so the whole physics you can represent in by just considering the part from 0 to 60 degrees. Then you have the prolate shape. You have here the oblate shape. Here you have the spherical shape. And in between you have what is called triaxial shapes. For what is coming in the IBM, you can only have either prolate or oblate. You cannot have a real minimum which is triaxial, except that in O6 you have gamma soft, but then it's a valley going from here to here. And so this we will use later on to make the extension not from 0 to 60 degrees, but with beta going from positive to negative. If I do from positive to negative, then I go from prolate to oblate. Yeah, so it's the same as going from 0 to 60 degrees. So that's important to know. And now the energy functional is defined by our Hamiltonians, which in between this coherent state, normalized as it should be, and which can now be evaluated for any value of beta and gamma here. And you look, of course, for the minimum, beta 0 and gamma 0 corresponding to your Hamiltonian. Here you see some examples. If you have the U5 limit, you see for beta, the minimum is 0. So it's no deformation, and it means you have a spherical shape. If you have the O6 limit, the minimum is not anymore beta equal to 0, but it's a certain value of beta. And if you go in the rotational case for SU3, you have a sharp minimum at a higher value of beta, showing that in this case you have a prolate rotor. So here I've listed again the kind of different cases you have for beta and gamma. Now, one thing which is very nice with the interacting boson system is that you can now, we have these dynamical symmetries. They are very nice for a theoretician. But most nuclei don't care about the dynamical symmetries. They are somewhere in between two of the symmetries. And the nice thing of the IBM is that you can have in the same model also the transitional nuclei in between spherical and deformed. While, for instance, in most of the other models, you have to change model depending whether you have a very deformed system or a very spherical. So in the IBM, you just have all these color shades for the nuclei. And so you can describe more or less all even nuclei in this case. Now let's come to the main topic, phase, shape phase transitions in the atomic nucleus. So what we are interested in is now to study how is the shape of a ground state of an atomic nucleus changing. As an example, we have a spherical ground state, so the nucleus is like a ball, or we can go over to a prolate ground state in which the nucleus is like a ball, but a rugby ball, not a normal football. So that's what we want to study in the ground state. Now, this is analog, and I think that's the important point, to phase transitions in solid state physics. So if I have a crystal, then the crystal can have a structure, a certain crystal structure, and then if you heat it up or you increase the pressure, then at a certain moment it changes its structure and it overcomes a phase transition. Now, this is the same which we have in nuclei, except that this is a quantum phase transition. This is a classical phase transition in which we now vary not the temperature, but the number of nucleons, the parameters in the Hamiltonian, eta and chi, and we observe that by the variation, we change the shape of the nucleus which we are describing from, for instance, spherical to deformed. If you remember from your courses, you have critical temperatures in the classical description of phase transition. So if the temperature is higher than the critical temperature, you have a minimum, for instance, here for order parameter at 0. And then if you decrease the temperature, you get a critical point in which you have, in essence, for a first order transition, 2 minima. And if you decrease the temperature further, then this becomes the deepest minimum. So if you now look at the value of the order parameter at the minimum, then you observe it's a constant, and then discontinuity, you get at the critical temperature a change of the value. So it means you have this is always constant. It's always 0 as a function of temperature. And then if you reach the critical temperature, then the minimum is going down. And if you look now at the control parameter corresponding to the value of psi at the minimum, then you have a jump. So it was always 0, and then suddenly you have a jump at the phase transition, which is a first order phase transition, and you get then another value which might increase as a function of the decreasing temperature. The second kind of phase transitions are second order phase transitions, in which you don't have really a second minimum, which is developing and taking over, but you have a more or less smooth evaluation of the energy functional as a function of the temperature. And what you observe in the case of a second order phase transition is that you have a discontinuity in the order parameter. So here it was always 0, and then here you get a discontinuity and you have an increase of the order parameter after the second order phase transition. So now there is Lev Landau. He made the theory for continuous phase transitions in 1937. He describes these phase transitions, and we were able to show that his theory is always also valid for nuclear physics in an article in 2002. Of course, there are differences between Landau's article and our application, but in essence, it's the same thing. And if you look in Landau and Lifshitz, where he describes this, he says there is even not an experimental example of his continuous phase transition theory. So this is not the first one, but there are more. But one is this phase transition. Now we have to compare. Language is a difficult thing in physics. If you are discussing with solid state physicists or other physicists, nuclear physicists, it's different language which is used. And so we have first to look what is the language of Landau's theory and what is the language of our theory. So in the case of Landau's theory, you have a thermodynamical potential, phi, which is a function of two external parameters, which are the pressure and the temperature. And it has one order parameter, can be the crystal structure, can be the magnetization, can be anything, which depends on the pressure and the temperature. So in our case, it's a bit more complicated because we have three external parameters: the number of nucleons, the values of eta and chi in our simple Hamiltonian, and then we have two order parameters, the deformation given by beta and gamma. So the task is now to find for every value of pressure and temperature the thermodynamic potential and its minimum. So the minimum will give us a value of psi at pressure 1 and temperature 1. And then we just look how it varies. If we have now another temperature, temperature 2, then the minimum will be not the same as here. It might be a little bit higher. And so we have to do that for every value of P and T. We have to construct this thermodynamical potential. Now, this we have to do also for our model. I don't want to give the details. If somebody wants to see them, I have them somewhere in the backup slides. But in the case of the simple Hamiltonian, Landau's theory gives the following solution. So we look at the value of beta, and we have allowed that beta can be positive for prolate rotors and negative for oblate rotors. And this is what you get out. So you plot, instead of P and T, you plot chi and eta. as the control parameters. You see here you have a part in which the value of beta minimum is equal to 0. And then at a certain moment, you get a first order transition. And then you have here beta being positive, and on the other side, beta being negative. So this side describes prolate rotors, and the other side describes oblate rotors. And in fact, if you work it out, I'm sorry. If you work it out, you can get the critical eta value to be equal to this expression. If n goes infinity, then it goes to 0.8. And the critical value for chi is chi equals 0. So this line corresponds to chi equals 0. And this line corresponds, if you take finite n effects, to this equation. So from that, we get this kind of new nuclear shape phase diagram in which I've presented now the dynamical symmetries of our simple Hamiltonian. And so we observe a first order phase transition here at chi equals 0.8 approximately. And we have also a second one, which is going from here to here at chi equal 0. And so these first order phase transitions, they make the change between a spherical nucleus, a prolate deformed, and an oblate deformed nucleus. And interesting, we have also a second order phase transition. Here, at this point, the second order phase transition takes place. And so we have called that the triple point of nuclear deformation, because if you're sitting here, you have the spherical, the prolate, and the oblate shapes more or less all together. So like a triple point. I just want to point out that this fact that you have here a first order transition and here a first order transition with at the intersection point a second order transition is exactly the prediction which Lev Landau made in 1937. And you can find it in the statistical physics part of Landau and Lifshitz. So the shape transition can be seen by, for instance, the ground state energies. So we plot here as a function of chi. I've indicated again where the dynamical symmetries are in the triangle. We just plot the energy of the ground state, absolute energy you get from the model. I've indicated with dashed lines the first order and the second order phase transition. I would like to make a remark because we are dealing with a finite number of, and this is even an unrealistic number for an atomic nucleus, 40 bosons, it doesn't give that. But if you have a finite number of participants, then these phase transitions, they are smoothed out. Yeah, so they are not sharp. If you go to n is 1,000 or 10,000, then this becomes really sharp. We will see some effects of this finite n dependence. So one way one can see these phase transitions in two neutron separation energies, they have been used already in the 80s to look at this kind of shape transitions between spherical and deformed, and they show up as a kind of plateau in the two neutron separation energies. So what we are interested is, for instance, the quadrupole moment, which is dependent on the order parameter beta. And so this is a more realistic with 10 bosons, and with 40 bosons is less realistic, but you see clearly how the quantum phase transition is much smoother for lower N than for much more abrupt for higher Ns. And so the quadrupole moment is one of the things you can experimentally use to find out whether you have such a shape phase transition. A very sensitive signature in particular is the BE2 from the second excited 2+ to the first excited 1+, which has a kind of peak at the phase transition. And so that's two things we can use. And that we have used in order to study the SU3 to SO6 to SU3 first order phase transition. So the signatures are negative quadrupole moments in the prolate part, then a very sharp change of the quadrupole moment, and then we have an oblate quadrupole moment for the oblate shapes. And as I mentioned, we have this peak in the BE2 from the second excited to the first excited. And if you take the ratio of the 4+ energy over the 2+1 energy, you also have this kind of dip at a phase transition. Phase transition is taking place at chi equal 0 or the O6 limit. Now, in order to check, you can look here, first of all, at the gamma dependence. So we start prolate, so minimum gamma 0. Then it becomes weaker, weaker. And then you have the O6 region where it's flat. So it's completely flat in the direction of gamma. And then you go over to the oblate, in which you have now the minimum at 60 degrees as a function of gamma. Now, experimental examples we looked for. So we're looking for nuclei which are lying on this axis. And candidates, we saw platinum-196 was the best example of O6. These are well-deformed prolate nuclei, like 180 hafnium. And so we have found a way through this phase transition going up to 200 mercury. Notice that, of course, for every different atomic nucleus, N is changing. Yeah, so we have to take account of N, so we cannot compare directly with the figures I've given before. But if we now look at the experimental values, we clearly see in the quadrupole moments, they start negative and big, and then they go over and become positive, not so big anymore. We're close to a closed shell, so to really have oblate deformation is more difficult. We see the peaked distribution in the BE2 value, and also in the 4:2 ratio, we see more or less, again, we're close to the closed shell on this side, so it's weakened off, but nevertheless, we can observe some of the signatures of the quantum phase transition in actual nuclei. There is another approach which I would like to mention by Franco Iachello. It's an approach which does not, there is a lot of confusion by it, but it doesn't rely on the interacting boson model. Iachello being the inventor of the interacting boson model, this is one of the reasons of the confusion. But he made analytic solutions of the collective model, the pure collective Bohr model, and introduced new symmetry, which he called X5, which is corresponding to the first order phase transition between spherical and prolate, and E5, which is corresponding to the second order phase transition, which we have in the interacting boson model. And the X5, at the moment, Franco proposed it, Rick Kasten and Victor Zamfir published an example in which in fact was measured in Köln. We put a European source during a whole Christmas weekend in front of a detector, And from that, that's in essence the basis of some of these observations, which were then used by Rick and Victor to show that this has the kind of X5 structure. So important is it's a parameter independent prediction of the energy, for instance, of the 0+ state and of the BE2 values. So after that, other examples were found and seems to confirm the existence of X5 in several nuclei. So all examples are measured in Köln by Rainer Krücken, by Dimitar Tonev, and by Oliver Müller. And if you compare as a function of spin, the BE2 value and also the energies, they more or less follow nicely the X5 prediction, except for dysprosium 156, where the BE2 values, the energies are agreeing with the model, but the BE2 values are more agreeing with the rotational model. Now there is something interesting because Libby McCutcheon and Rick Aston predicted many years ago of a kind of relation of what they call the P factor, and it's a kind of equilibrium between forces making deformation and forces making spherical shapes. And you see these rings here. This is where they expected to observe the transition between spherical and deformed. So the examples I gave you before are exactly these nuclei, but you see also here there are should be candidates, and so that is what we also studied in Köln using the orange spectrometer and our plunger device. And so I take one example, which is 178 osmium, which also nicely agrees with the X5 candidates. So because of that, you can now place many different nuclei. So this is only an example of nuclei close to X5 on the triangle, but you have also other studies which place a lot of transitional nuclei inside the triangle. Now I come to something more specialized. Up to now, we were discussing only even nuclei. Now, even nuclei are only 1/4 of all nuclei. 50% of all nuclei are nuclei with an odd number of protons or an odd number of neutrons with an even number of neutrons and an even number of protons. So odd A nuclei. And now this is, of course, a more difficult problem because you have now an N boson system and one uncoupled fermion. So you have a boson-fermion system. The last nucleon, which is the uncoupled fermion, can have different single particle orbits. And so what we would like to have is to have a simple Hamiltonian corresponding to the one we had before in order to study phase transitions in odd A systems. Now, in the 80s, dynamical supersymmetries were developed for nuclei. So this was in the time of my PhD, and so I also was involved in that. So one of these supersymmetries is the U612. 6 corresponds to the number of bosons, so the 6 magnetic substates of an S and a D boson. 12 corresponds to the number of magnetic substates if you have the allowance to occupy a J1/2, so 2 magnetic substates, J3/2, so 4, and J6/2, so 5/2, so 6 magnetic substates. The sum of it is 12. So we have a 12-dimensional fermion space and a 6-dimensional boson space. Now the trick you use in these boson-Fermi symmetries is that we have now our boson system with L equals 0 and 2. And then we have our fermion with 1/2, 3/2, and 5/2. But we now consider this as being a pseudo spin L equals 0 and 2, and a pseudo spin 1/2. So this makes 0 and 1/2 makes 1/2, and then 2 and 1/2 makes 3/2 and 5/2. In group theory, it corresponds to a reduction going from U6 and U12 to U6 times U fermion 6, that's the pseudo spin part, and U2. And now these two groups you can combine to a boson plus fermion group, and you can embed this guy here into a superalgebra, which is shaded Lie algebra. Don't know what I did now. Oh, yes. So we can embed this in the superalgebra. This makes that it now generates, depending on the reduction rule, from the supergroup to the normal group, it generates a spectrum in an even nucleus or a spectrum in an odd A nucleus. The parameters have to be the same in both cases. And then finally, because we have this UB plus F6, we can recover the three different dynamical symmetries, basic dynamical symmetries of the IBM-1. And then at the end, we have here the SO boson plus fermion 3 group, and we have this pseudo spin with 1/2, which we have to couple to come to this spin group, final group. Now, this is the most general Hamiltonian you can write in this supersymmetry, but what is important is that you can now extend the Kasten triangle for odd A nuclei. This was proposed a long time in 1985 by Dave Warner, Piet van Isacker, myself, and Alison Bruce. And we get an equivalent Hamiltonian, which has here the ND equivalent part, which is the Casimirov fourth order of the boson plus fermion U5 group, and the quadruple part is also for bosons or boson plus fermions. Now, if you look now at the ground states in this same transition we looked before, this was for the S and D boson system. We go from SU3 over SO6 to SU3 bar. And so that's the kink you have in the ground state, first excited 0 plus and so on. And then you do the same now for the fermions with 10 bosons and 1 fermion. You observe similar structure. You have a kink here. And so you see that you also have a first order phase transition in the case of the odd A nuclei. Now, there are some differences, and they are quite interesting. This, just as an example, for U5 to SU3, you also have the first order phase transition in this one. Now, there are some differences which are interesting. First of all, you can extend now the Kasten triangle with for odd A nuclei. And so, as I mentioned, there are some interesting differences, especially for an ex-theoretician like me. So if you look here, you have no crossing of levels. There is level repulsion if you're not in a dynamical symmetry. It means there are no extra quantum numbers. If you are at SO6, then you see here a real crossing, and here a real crossing also of two excited states. This comes because they have different O5 quantum numbers, and so they can cross. Now, if we look in our supersymmetric description, then we see outside the dynamical symmetry, real crossings everywhere. So this is quite unexpected and interesting for a theoretician like Piet and me from time to time. So here I make a zoom around 0. So we have now our solutions, and we see real crossings outside the dynamical symmetries. And so in order to investigate where they are coming from, we can now add a perturbation to our computer code by just lifting the energy of the third 3/2 a little bit. So a perturbation. And as soon as we switch on this term, you see the real crossing disappears. So it means that there is a quantum number here, which is not there. And if you now look at the structure of our symmetry, then we see that independent of where I am here in these dynamical symmetries, I have this conservation of this O3 pseudo L quantum number if I use this Hamiltonian. If I use now this perturbation, I remember the pseudo L was associated with 1/2, 3/2, 5/2 being 0, 2 coupled with 1/2. So I break now this symmetry, and so I have no crossing anymore because L is not anymore a good quantum number. And so there is even more to the story. If I break now the symmetry in the same amount for 3/2 and 5/2, I recover the L quantum number and I get again real crossings in our model. So that's for what concerns doesn't want? Eh? Can I try that? Doesn't do anything. Oh. No, I'm sorry. Yeah.
Just a second.
I'm in. Okay. So I hope it's. Can I try to go to the next one? Yeah. Okay. So now let's remove to Earth. Yeah. So let's see whether you find some applications to real nuclei. So one of the thing which is a stringent condition, you need to have dominant J equal 1/2, 3/2, and 5/2 orbits for either the neutrons or the protons. And that, of course, you don't have over the whole nuclear chart. You have it only in certain regions. And then associated, you have to have a phase transition in the even-even system. And so there are a couple of examples. Selenium arsenicum for U5, close to U5 nuclei. Then ruthane and rhodium for between U5 and SU3. And we will focus to the wolfram and platinum because we saw before that going from hafnium to mercury, we could describe a prolate to oblate phase transition. And so we would like to focus on this. And there is some old work by a long time ago, which describes the odd neutron nuclei in the wolfram platinum region. There is a perturbation term here. The rest is our Hamiltonian, as I introduced before. And so here you see growing from 199 mercury up to 191 osmium, the predictions of the model. And you really see that there is a phase transition acting here around 195 platinum, because the ground state, which was 1/2, becomes then 3/2, and the level density is also compressed in this case. So there are some examples, there are only few examples studied up to now of odd A nuclei showing these phase transitions. So let's come now to the last point, which is level dynamics and phase transitions. So up to now, we only looked at more or less the ground state and few excited states. Now we look at what is happening with higher excited states in the level densities. So I have here the example for 30 bosons. We look at the excitation energies of the 0+ states up to 2.5 MeV as a function of eta, our control parameter here. Phase transition is at 0.8. We go from rotational to vibrational. And so we normalized everything with respect to the ground state energy. And so what you see is a compression of the level scheme. These are all 0+ states. They are not realistic compared to atomic nuclei because we have 30 bosons. You see a kind of compression at the phase transition of these 0+ states. So the question is there something for lower number of N comparable which can be observed? For that, we go to München, to the Q3D spectrometer. It's a magnetic spectrometer, and it's extremely well suited to study 0+ states. It has an excellent energy resolution of 4 kilo electron volt for 15 to 20 mega electron volt tritons. And so 8 nuclei in the Earth region were systematically studied up to 3 MeV in a collaboration with Yale, Ricaston, Bucharest, and Surrey. So this is the result. These are all 0+ states, which are for sure measured. That's the full lines, and possible candidates are the small lines. And you see that the level density is the highest in 154 gadolinium. That's this. And this is exactly where we saw before we have this phase transition. And so if you plot it, then you find a kind of experimental, more or less, proof for the phase transition in the number of observed 0+ states below 2.5, which really peaks in 154 gadolinium, if you look at the different nuclei. Okay, now let's continue. There is a lot of theoretical interest in these phase transitions for excited states. So here I plot this simple Hamiltonian again, and now we look at a transition where we have O6 in the quadrupole operator, and we go from spherical to O6, and then we have eta equal 0 up to 1, 1 being spherical, here the phase transition, and then here the O6. And so we've now plotted the energies of the 0+ states, and already soon we found something amazing, which we didn't understand for quite a long time. That if you look at the energy 0, you get a structure, a very strange structure. This kind of pentagons of empty places where there are no 0+ states. And if you zoom into it, then you see that they are crossing here. Outside more or less the dynamical symmetry, they are crossing. Now you can do that because you have the quantum number V, as O5 is a subgroup of U5 and O6, it's conserved for the whole transition. And so here you see a zoom, you have this crossing, and if you now write down in more, just one moment. Yeah, so these are the associated values of V. It's always a multiple of 3. So you have here 0, and then 0 and 3, they cross here, and then 0, 3, 6, they cross here, and so on. So there is interesting things concerning phase transitions, starting at a phase transition, but appearing very highly in the excited spectrum. Now, what is the reason? The reason is what is called monodromia. So you have to imagine if, let me get this. If you have a sombrero-like potential, which is known for many kinds of physics. So if you are here, then you feel like being in a parabolic potential. But once you get here, you get the whole place, more or less, and everything is filled below. And so now this feels like you're in a different kind of potential. And this effect is called monodromia. And so you have a different kind of structure for states above the top of our sombrero and states below the sombrero. So in our case, we have this kind of thing that we have more or less a spherical at 0 energy, and we have this gamma soft at negative absolute energies for the ground state. And so this is, in essence, explaining why we get this very strange structure starting at the 0 energy. So if you look at it, if I'm inside this part of the sombrero, then I have these solutions. So we are at eta equals 0, so we are at 0.6. You get this kind of, for the different values of the quantum numbers, you get this kind of behavior inside the sombrero. And then if you're now at 0.6, this is this value here, and around the energy of 0, then you have a change of structure. This below part looks like the sombrero one. And I'm sorry. No, I know. Yeah. So if you're now at 0.6, you see something is happening here. Around 0, the structure is changing of the energy states. Above 0, they look like that. They look like if you have a spherical structure with eta equal 1. Below 0, they look like this, like the 0.6 structure. And there is a kind of point defect at the energy 0. And you see they are trying to align themselves, changing from one structure to the other one. And this is when they align themselves, they are creating these gaps. So these gaps are related to the fact that if you have an excited state phase transition, a certain moment you are at this energy and your potential is completely changing at this energy. Okay, so now I come to my conclusions. I think I did too long. So the shapes of atomic nuclei undergo quantum phase transitions, which are smoothed through the finite particle number. And the IBM provides a very realistic and very rich and very simple model to study these shapes. And of course, we have experimental data confirming, for instance, these X5 nuclei. And finally, new field is popping up. It was developed not by me anymore, but by some of my collaborators afterwards in looking at excited state phase transitions. So my collaborators are given here. I would like to pinpoint the main collaborators, which is especially Pavel Čenar from Prague University, Rick Karsten from Yale, and Stefan Heinze from my group in Köln. There are some general references which you can take a look at. And then I will not say it in Bulgarian, but thanks a lot for your attention.
Thank you. Thank you. Do you have any questions? Go ahead.
Let's go back to 196 Platin. Do we really have a good example for O6 symmetry?
Yes, I will comment on that. I will first of all use one comment which is coming later in the talk. Okay. So the main objection against platinum-196, which is sitting here, is that it has a quadrupole moment, which is forbidden in the theory. Yeah. So that's one thing. But if you now look at the systematics in the quadrupole moment, you see that this change from here, -1 up to 0.5 or something like that, is very rapid, yeah? So you're moving only from osmium to platinum-194, 196 in this domain, and so you're not really hitting the part where the quadrupole moment is 0. But on the other hand, the other selection rules, like the ones on the B2 values, we have shown that it's very small. It's not 0, but it's very small.
But the same you will get if you have a shape coexistence. The same B2s, the small B2s.
But in platinum-196, no.
Yes. If
yes.
You go to the level scheme.
How do you get there a shape coexistence? So there I agree strongly. You can have in much lighter platinums, you have shape coexistence models which are used, but not in platinum-196. So what you would expect then is a kind of intruder structure, so additional 0+ states. And if you look at what is known for platinum-196, I'm sorry, I'm now too far. If you look what is known for platinum-196, there are no extra 0+ states. So, I mean, we're not talking about platinum-182, where you have shape coexistence.
Okay, but we also know that on the top of the transition between 2+ and the 0+ in sigma equal n-2 is stronger.
Here, this one.
Yes.
Yeah.
This, and what you can measure is the B2 from the 2+ to 0+.
Yes.
And they're small.
Yeah.
But you can have the same signal if these are different structure as put it better. Okay?
Yeah, okay.
And then we know that from 2+ to 0+ in sigma equal n-2, this transition is stronger than the transition from the 2+ to 0+ from the ground state.
You mean this one?
Yes.
Yeah. But if I remember well, this is not not known. Is it known?
It's not published, but it's known.
Ah, yeah. So it's hidden.
No, you know it, yeah, you know it.
So, but I would say you expect shape coexistent at mid-shell, and mid-shell is 182. This is really very far from mid-shell. So I would not expect it.
Even if you go to the slide with the examples for X5, we have so many examples for X5. Right?
Mm-hmm.
And if you compare now to 06, virtually we have only one candidate for 06.
Which is 196.
196,
yeah.
And this is questionable.
Yeah.
So what's the reason? Both of these are first order phase transitions.
Yes. Yeah.
So why do we have so many X5 examples? And
yeah, but this is not X5, eh? No, because we have
my question is
because we have many more rotational nuclei available on the market than gamma unstable. I mean, if you go to a certain moment, I've shown this McCutcheon-Karsten classification. Yeah. I have to go through it again. Yeah. I mean, we know all these are deformed nuclei. These are spherical ones here at the edge, are spherical ones. And this is the region where you have this transitional nuclei. Yeah? And so there are much more deformed and spherical nuclei to make the phase transition. So what we saw is this one, this one, this one, and this one. They are examples of X5, and also osmium there is an example of X5. So I think this is the reason, because you have a much larger availability of nuclei. Yeah. Yeah. Yes.
Well, it's possible from this approach that is based on symmetry of bosons to extract quantitative value for the mean field in the nuclei.
We do it not going from the IBM to the mean field. So the IBM is essentially a phenomenological model, as I show with a limited number of, but we do it since years in the inverse direction. So I collaborated quite a lot with Kosuke Nomura. And so he takes also the energy functional, which you can calculate from a mean field approach, the 5D CH approach, or 2S or 2M. And you get this energy functional. As I showed you, you get also energy functionals by the coherent state approach from the IBM. And so what he does, he fits now to the mean field approach the form of the energy functional, and then he implements it in the IBM, this same energy functional, or fits to it, and then he can do an IBM calculation. Yeah. And the advantage is he doesn't have to project on particle number, on good angular momentum. All these very difficult things are not there. And so this Kosuke Nomura has done for many regions of the chart. But we cannot go in the inverse direction. So to say we can fit an Hamiltonian in the IBM. We get also a potential function. And now we can try to make a fit of a mean field calculation to this potential function. But that's more complicated.
Well, but the interaction has to be derivative of the mean field, yeah. If you have these bosons, yeah, this interaction has to come from the mean field,
yes,
value
yeah.
of the mean field.
Yeah, but we don't start with the mean field. We start more or less with the phenomenological. Except when we do this a la Nomura, then we start from the mean field, we get a mean field potential, we fit this energy potential to an IBM potential, and we have then the IBM calculation. So he has done that quite systematical. He has done that for even nuclei. He has done that for octopole deformation. He has done it for odd A nuclei. He has done it for shape coexistence. So there is a whole zoo of going from mean field to IBM, not the inverse.
More questions? Can I ask?
Yeah. Yes.
We have a reduction from certain groups to lower.
Yes.
Is it possible to have a reduction from one, say, O6 or U6 to supergroup dynamic?
No.
Is it forbidden?
As far as I know, it's not done. Because what we do is we use, in fact, the supergroup as a kind of embedding group. Yeah, so we have a product of a boson group and a fermion group, and we put the supergroup on top of it to embed both in it. And the prediction of supersymmetry is then that if we go in the inverse direction, we have the super E-rep giving an N boson system, N minus 1 plus 1 fermion, N minus 2 plus 2 fermion, and so on. And so the Hamiltonian has the same parameters. The structure of the Hamiltonian is different because once...
What I mean is if you consider the even number of fermions bosonized.
Yeah.
And then to break this, to have a odd number of fermions.
No.
Possible? No.
No. As far as I know, it's not done. Yeah. So it's always from the top to the bottom. Yeah.
Thank you. More questions? Okay, let us thank again to our speaker. Thank you.
Yeah.
So, thank you everybody for attending our seminar. Thank you, and tonight, see you.